Hi everyone, we'll be starting class in 1 to 2 minutes time. Hi, good afternoon everyone, and today's lectures are going to be on the continuation of the Bode Plots lecture that we did yesterday. Now in yesterday's lecture we basically saw the 7 examples that were introduced to you that basically gave us an indication for each one of those examples. How do we go about obtaining the magnitude and phase plots? And those 7 examples are quite important for when we're starting to deal with complex systems today in this lecture as to how to resolve the magnitude and phase plots for those complex systems in particular. So let's get to it, and we'll actually start seeing this in a practical example of how it can be applied. So we need to revisit the single pole transfer function here in particular, and the reason for this is that we know that we start off with the h of s function here, where we're being p divided by s plus p. In this case, p takes the value of 10 for our example system here. And then we would have standardized its h of s and then converted it into j omega to obtain the actual standardized representation here in the j omega domain. And the reason why we do the standardized h of form is because it gives us a baseline. So basically, that standard form makes the low frequency here for the omega divided by 10 component asymptote at the 0 decibel line on the y-axis. And we also know that if we did our magnitude versus frequency and phase versus frequency, our plot for the magnitude versus frequency for anything before the pole, it would have been 0 decibels per decade. But for everything after the pole here, it's going to be a gradient of minus 20 decibels per decade in particular. And because we're doing straight line approximations, we just considered before and after. We don't consider this minus 3 decibel change here, which is a true plot, because we're just going to be dealing with straight line approximations in particular. The phase plot is also what we've seen in yesterday's lecture, is everything before the pole is going to be at 0 degrees, and everything after the pole is going to be at minus 90 degrees. For this particular case, when we connect these two transitions, we represent this by a vertical line here at the pole itself. The true plot, as we can see here by this red dotted line, indicates how the transition will actually occur, but because we're doing straight line approximations, we represent this transition just by this vertical line here. Like I said, just because it is an approximation of the actual plot. So for anyone who's interested in like seeing how you can actually do Bode plots in MATLAB or Octave, or any other related MATLAB substitute that there may be, these are the commands actually to how go about doing the Bode plots themselves. And they'll work for MATLAB and for Octave, and Octave is free if I remember correctly. So you can use either one to experiment with your Bode plots and obtain your transfer functions and then obtain the relevant Bode plots in particular. to see what the magnitude and phase plots will look like for any particular system. And the figures here are the result from MATLAB itself, showing the magnitude plot and the phase plots here. We can see here that because of the pole at 10, that would actually represent a -3 decibel drop at this point on the magnitude graph, and it will represent that 45-degree change here on the phase graph in particular. Now, what happens when we introduce a gain with our standard form that we just observed for a single pole transfer function? So instead of the numerator here being 1, it's now going to be some constant real value here, a. And how does this affect our magnitude versus frequency plots and our phase versus frequency plots? So the plot basically looks the same, but the only key difference is that it will no longer start at that 0 decibel line. Because we have this a component here being a real number, that means the starting point for the graph now is going to be 20 log of a. And whatever value that is, that's going to be our new starting point for our graph. The graph will still take the same shape as we've seen before. It's just, for the magnitude plot, it's just going to shift up or down depending on that 20 log a value in particular. So, for this particular Bode plot that we see here, we see that instead of starting at the 0 decibel line, it's going to start at the 5 decibel line instead. And we also know that if we take -3 of that 5, that's going to be at 2 decibels. We can obtain where this actual pole lies as of such in particular. Similarly, we can also watch this such that we look at the -45-degree line here on the phase plot, and we see where it actually intersects with one of these poles here in particular to see where it actually occurs. So you can actually verify, double check this by saying, okay, at the 2 decibel line here, we want to see where the actual pole value is, and at the -45-degree line, we want to see where the graph intersects with that -45 to obtain our actual value of our pole. And because we know this is 5 decibels, that's going to be 20 log of a equals 5. You can reverse the equation and solve for a, and you'll obtain your transfer function for your following Bode plot. So for homework, I would like for you guys to actually attempt this and see what transfer function you obtain from just reading this Bode plot in particular. Alright, so for our example here, which is example 9, this is actually where we start encountering complex systems. And the complex systems, basically, we'll see here that the numerator is going to be some function of s, and the denominator is also going to be a function of s. And the degree of the numerator and denominator can be any form. So this could go up to like cube, this could go up to like quartic. Same thing with the denominator, it could go up to cube and quartic as well. And no matter what the degree of the numerator and denominator is, it's going to be the same approach that you take to resolve the Bode plot for the complex system, which we're going to see in the next few slides. So we're going to be starting with the magnitude versus frequency graph first in particular, and then we'll move on to the phase versus frequency graph, and we'll see how basically we move from a complex system to a series of simple systems, and how do they compound with each other to form the overall magnitude plot and the overall phase plot input. So our first step for our h of s system here is to factorize it. Our second step is you can either convert it to the j omega domain, or you can standard form it immediately by just dividing throughout by each one of those pole values here in the brackets. So for our example here, we convert it to the j omega domain first. The third step is where we convert it into standard form following that second step. So that means when we do this conversion, here in particular, and we do the standardization, this equation here will now become 40 j omega divided by 4 into j omega divided by 4 plus 1, and then 10 here into j omega divided by 10 plus 1. And if we simplify that, that'll become 40j omega divided by 4 by 10, which will give us 40, into 1 plus j omega divided by 4, and then 1 plus j omega divided by 10. And these 40s here, basically, they will cancel with each other. And that gives us our result here of j omega divided by 1 plus j omega divided by 4, multiplied by 1 plus j omega divided by 10. And converting the entire equation into standard form. So, because this here is just j omega, and the constant value in front of this j omega is just 1, this is why we say refer to it that there's a gain of 1 present here on the numerator. So, if we take 20 log of 1 basically resolves to 0 for any base. So that's just going to be the low frequency asymptoting at the 0 decibel line here, which gives us a starting point for a magnitude graph. The next step after we do the standard form is to break the system equation that we have here into a series of subsystem equations. And in each one of these subsystems, we're going to be plotting their individual magnitude graphs, and then we're going to be watching how do these compound with each other, in particular to form our resultant graph for entire h of j omega here. So, because we have one component here on the numerator and 2 components on the denominator, that means we can break it into 3 subsystems. So h1 j omega here will just be j omega, represented on numerator component. h2 j omega will just be 1 divided by 1 plus j omega on 4. And h3 j omega will be 1 divided by 1 plus j omega on 10. And if we multiply h1, h2, and h3, we'll just get back hj omega here in particular. So keep in mind that we just broke hj omega here into h1, h2, and h3 j omega. And we're going to be plotting the magnitude graphs for each one of these h1, h2, and h3. And we're going to observe the effect, how do they compound with each other, to form the resultant magnitude graph for h of j omega here. So our first step that we do is that we set up our axes in particular when we actually start doing this. So remember, our y-axis here is going to be in decibels, and our x-axis here is logarithmically spaced. So this is going to be 10 to the 0 to 10 to the 1 and then 10 to the 2. And remember, the spacing in between these is going to differ between each power of 10. So in this case, the spacing here is just going to be 1, but in between 10 to the 1 and 10 to the 2 here, the spacing here is going to be 10 accordingly. Once we draw our axes, we then put our pole values in, because these are going to represent our subsystems in particular that we just now have. For omega equal 4, this is going to represent our H2 system, and for omega, or H2 subsystem, sorry. And for omega equals 10, this is going to represent our H3 subsystem. Our H1 subsystem was just j omega, and that basically just means that we start at the 0 decibel line here in particular. So the h1 j omega here equals to j omega. Oh, sorry, I said the wrong thing earlier. The reason why we started the 0 decibel line here is because the h1 j omega, the constant in front of that j omega is just 1. So that means we basically started at 0 decibel per line here. And we watched that from this 10 to the 0 power here in particular where we started. Now I know the graph here basically extends backwards from 10 to the 0 and it goes to negative powers here. So like 10 to the minus 1, 10 to the minus 2, and so forth. But when you're drawing your Bode plot in particular, you start at 10 to the 0 here on your x-axis. So h1 j omega here equal to j omega. This basically is the example we saw, which was basically a simple 0 at the origin. And the magnitude graph for that simple 0 at the origin was just basically a linear line here with a constant gradient of positive 20 decibels per decade. So we basically draw this line for h1 j omega for our entire graph here. For h2 j omega, we basically know that for anything before that pole value, being anything before omega equals 4, it's going to be 0 decibels per decade. And for everything after that pole value here, it's going to be a constant gradient of minus 20 decibels per decade. Similarly for H3, everything before omega equals 10 is going to be 0 decibels per decade. Everything after omega equals 10 is going to be minus 20 decibels per decade, in particular for the gradient of the line. Now that we have our three subsystems plotted here, we're going to be watching in particular the compound or the superposition of everything before this first pole here, in between these two poles, and then after this last pole here, to get our resultant final magnitude graph for our entire Hj omega system. So when we do this in particular, we basically watch this such that, okay, the black line here represents our result, but I'm going to explain to you how do we obtain this black line. For everything before omega equals 4, we're going to be summing the gradients in each one of these lines to get our result. So we know H1j omega here, the gradient here is positive 20 decibels per decade, but for H2 and H3, it's 0 decibels per decade. So that's going to be 20 plus 0, which gives us a result here of plus 20 decibels per decade. I want to write this on the slide so that you can keep track of it. This part here, which is in between omega equals 4 and omega equals 10, we're going to be summing each one of these gradients here for H1, H2, and H3. So this H1j omega line, this continues throughout the entire graph, just keeps on going. So in between omega equals 4 and omega equals 10, this is going to be positive 20 decibels per decade here. So we're going to write this in for our result. That's going to be 20 here. We then watch our H2 subsystem here, and we see that the line here in between omega equals 4 and omega equals 10 has a gradient of minus 20 decibels per decade. So we're going to factor that in here as well. That's going to be minus 20. And then we watch here for H3 j omega subsystem, sorry. And we basically see here that the gradient of this line for H3 is going to be 0 decibels per decade. So we just add in that 0 in particular. And the result here is just going to be 0 decibels per decade. And then finally, for everything after omega equals 10, we're going to be watching the summation of the gradients again for H1, H2, and H3 subsystems. So H1 here just keeps on going throughout the entire system. So that's going to be positive 20 decibels per decade. So we're going to write that in. Hold on. Let's get a little bit neater. And then our H2 subsystem, we basically see for everything after omega equals 10, the gradient of this line here is minus 20 decibels per decade. So let's write that in as well. And then for H3 subsystem, this here is also minus 20 decibels per decade after omega equals 10. So this is, we want to factor in this minus 20 decibels per decade into our result here. So let's write this in. And we can see here that the summation of these gradients means that we get an end result of minus 20 decibels per decade. And basically, by doing the superposition of each one of these subsystems before the poles, in between the poles, and then after the poles, the summation of the gradients here basically gives us the resultant gradient for our Hj omega system in total. So that's how we obtain our resultant magnitude graph here in particular. So before I move on, are there any questions in particular as to how did we obtain this resultant magnitude graph using these H1, H2, and H3 subsystems to form our result for the entire Hj omega system? Alright, sure, yeah, I can reiterate how we initially plotted the graphs. So, when we initially plotted the subsystem graphs, this was basically after we broke our Hj omega system here into relevant subsystems here. So, we just basically watch how each one of these subsystems here multiplied with each one another to form our H of j omega. So we watch the numerator component here and say this was H1 j omega equals to j omega. And then H2 j omega is just going to be 1 divided by 1 plus j omega divided by 4. And H3 j omega here is 1 divided by 1 plus j omega divided by 10. Each one of these subsystems here are basically going to be the examples that we saw in yesterday's lecture for how do we obtain the resultant magnitude graphs for each one of these. So this H1 subsystem here is a 0 at the origin, and we know that that's basically going to be for a magnitude graph that's positive 20 decibels per decade throughout the entire system. So that's going to be positive 20 decibels per decade for this H1 j omega subsystem. H2 j omega is basically a single pole on the denominator, and that's basically was in example 7 in yesterday's lecture. So everything before the pole is going to be 0 decibels per decade, but everything after the pole is going to be minus 20 decibels per decade. Similarly with H3 j omega, it's going to be the same thing. Everything before the pole here, which is omega equal 10, it's going to be 0 decibels per decade, and everything after the pole is going to be minus 20 decibels per decade. So each one of these subsystems here, you won't have to go back to the first lecture to see how do we plot the resultant magnitude graphs for each one of these subsystems. So when we plotted those in particular, because H1 j omega here is just going to be 20 decibels per decade, H2 j omega here is going to be 0 before omega equals 4, and then after omega equals 4 it's going to be minus 20 decibels per decade. And H3 is going to be 0 before omega equals 10, and then minus 20 decibels per decade for everything after omega equals 10. And we basically just sum the gradients before the first pole, in between the two poles, and then after the last pole here in particular. So before omega equals 4, I'm getting to the additional questions here. We basically see here that the H1 j omega gradient here is 20 decibels per decade. But H2 here and H3 here are 0. So that's going to be 20 plus 0 plus 0, which gives us 20 decibels per decade here. In between omega equals 4 and omega equals 10, this H1 j omega line is still going throughout the entire graph. So H1 j omega here is going to be 20 decibels per decade. The H2 j omega graph here, at this point in between omega equals 4 and omega equals 10, is going to be minus 20 decibels per decade. So we put in that minus 20 here. And then the H3 j omega graph here, it's at 0 decibels per decade. So we add that 0 in as well. That's 20 minus 20 giving us a result of 0 plus 0 giving us 0 decibels per decade. But the final part here, which is after omega equals 10, this H1 j omega graph, remember this still keeps on going throughout the entire graph. So this is like just going all the way up with a constant gradient of positive 20 decibels per decade. So H1 here, the gradient is going to be 20 decibels per decade because that just keeps on going throughout the entire graph whatsoever. H2 here, it's minus 20 decibels per decade for its gradient. So we put that minus 20 here. And then H3 here is also minus 20 decibels per decade. So we put that minus 20 decibels per decade here. So 20 minus 20 will give us 0, and then minus 20 will give us a result of minus 20 decibels per decade. So just to visually represent this, this line here keeps going throughout the entire graph. It doesn't stop there. It just keeps going throughout the entire graph as is. That basically is how do you obtain your final resultant magnitude graph here for h g omega using the h1, h2, and h3 g omega subsystems in particular. Right. Are there any further questions? Alright, it doesn't seem like we have any further questions, so that basically is the end of the magnitude plot for our example complex system here. But remember, this is just only one half of the Bode plot. We now are going to move on to the phase plot in particular. So before I move on to that, this basically gives you the MATLAB commands here for how do you obtain the transfer function and then the resultant Bode plot here for that magnitude graph in particular. And we basically see that the straight line approximation is somewhat close to the actual true magnitude plots for this representation here. So it basically gives us an approximate idea of how the actual Bode plot is supposed to look like, because like I said, it's a straight line approximation. Alright, so for the phase plot, we basically do the same thing, but we're now going to be focusing only on the angles of each one of those subsystems, being h1, h2, and h3. So we're going to plot each one of those onto our phase plot here. So we set up the axis first. So you can decide how do you want to plot the y-axis here, if you want to have negative angles or if you want to deal with positive angles. That is perfectly fine. Either way is fine when you're setting up your y-axis here. The x-axis is similar to the magnitude plot, where it's going to be logarithmically spaced. And remember, the spacing between these are going to vary. So for between 10 to the 0 and 10 to the 1, it's going to be 1. But in between 10 to the 1 and 10 to the 2, the spacing here is going to be 10 and so forth because of that logarithmic spacing. So we want to be plotting the individual phases for H1, H2, and H3 subsystems in particular. So our H1 being j omega, that basically means that it's going to have a constant phase of 90 degrees throughout the entire subsystem. For H2, which was at omega equals 4, everything before omega equals 4 is going to be 0 degrees, but everything after omega equals 4 is going to be at minus 90 degrees. And the sharp transition here is going to be represented by this vertical line. For H3, is everything before omega equals 10 is going to be at 0 degrees, and everything after omega equals 10 is going to be at minus 90 degrees. So, okay, let me go back one step. and let me annotate this so that way you guys can keep track. This is H1, blue line here is H2, and the purple line here is H3. So we basically do the same thing as before, where we just basically sum everything before the poles, in between the poles, and after the poles. So let me annotate one more thing here, so we can also see this. So that's at 4, and we know this one is here, it's at 10, so I don't need to annotate that. Alright, so before omega equals 4 here, when we watch H1, H2, and H3, we just basically see that H1 here is at 90 degrees, but then H2 and H3 here is basically at 0 degrees. So if we sum those, for this part here, that's going to be 90 plus 0 plus 0, so it gives us a result of 90 degrees. In between omega equals 4 and omega equals 10, we have H1 here being at 90 degrees, H2 here is at minus 90 degrees, and H3 here is at 0 degrees. So let's write those in. So H1 was at 90 degrees, H2 here was at minus 90 degrees, and H3 here was still at 0 degrees. So that end result here will just be at 0 degrees. And then after omega equals 10 here, H1 is still at 90 degrees, but H2 here is at minus 90 degrees, and H3 here is at minus 90 degrees as well. So let's write those in and see what's the result going to be like. That's 90 degrees for H1, minus 90 degrees for H2, and minus 90 degrees here for H3, which gives us an overall result of minus 90 degrees. That's how we obtain our overall phase plot for the H of j omega system using H1, H2, and H3 subsystems in particular with their individual phase plots. The last point to note is that when you're doing the phase plot, it is required of you to actually put down the angle equation for the entire phase plot. And basically it's just a summation of the angle equations for H1, H2, and H3 here. So H1 was basically it was 90 degrees, so we just say 90 degrees here. H2 here, if we did the angle equation for that, was minus tan inverse of omega divided by 4. And the reason why it's minus tan inverse is because it steps down to negative 90 degrees. If it stepped up, it would have been positive tan inverse instead. So a step down here on your phase plot, it's going to be minus tan inverse of omega divided by the pole value. A step up is going to be positive tan inverse of omega divided by that pole value instead. So for our particular case, H2 here, because it steps down by 90 degrees, is going to be minus tan inverse of omega divided by 4 because it occurs at the omega equals 4 here for that pole. And then H3 is also stepping down here in particular by minus 90 degrees. So that's going to be minus tan inverse of omega divided by 10 because that's the pole value at which it occurs. So you basically just add H1, H2, and H3, the angle equations, to get the overall angle equation here for Hj omega in particular. And that basically is the end of the phase plot. So are there any particular questions regarding this phase plot before I move on to throughout the entire lecture? Alright, so in yesterday's lecture, I explained that briefly, but I also have to explain it back again so that we can understand. So you know when it steps down when you have a pole value, meaning that the pole value is basically on the denominator. So let's backtrack a little bit here so I can explain what I'm talking about. Right. So basically, the H2 subsystem here, the pole value here is on the denominator. And, well, that's the reason why we call it a pole value. If it was on the numerator, it would have been a 0 value in particular. So, once we have this pole here on the denominator, that means it automatically steps down for the phase plot. If this was on the numerator instead, being like, if this was inverted, being 1 plus j omega on 4 on the numerator, all divided by 1, because it's on the numerator, it steps up instead. So that's why we end up getting that end result in particular. And if you're still a little bit unsure about it, check back the last two examples in particular in yesterday's lecture. I'll explain how you know when it steps down and when it steps up. Because for pole values, being that the root is on the denominator, it's basically going to be negative. But for 0 values where the root is on the numerator, it's basically going to be positive. So positive steps up, negative steps down. Let's get back here. For the last part where you're asking if it's going to be 90 plus 0 minus 90. Or did you mean for the in-between part? The in-between part is basically the same thing. This was 90 degrees here. The H2 system was minus 90, and then the H3 system here was at 0. Similarly, for the last part here, this was 90 degrees, minus 90 here for H2, and then minus 90 here for H3, giving us a result of minus 90. And we did that in order for H1, H2, and H3. So if you're asking for this part here, particularly in between the poles, it's the same thing. It's just reordered in a different way. There are two corner frequencies for that magnitude versus frequency graph in particular because of the subsystems. There won't be one corner frequency, and the reason for that being is that we saw that the denominator was of order 2. So basically, the corner frequencies here are represented by those pole frequencies in particular, or those pole values. So we have two corner frequencies here, being omega equal 4 and omega equal 10 for that magnitude graph. The only time when you'll have a single corner frequency is when the entire system equation is of order 1. But when you start increasing in orders, you will no longer have one corner frequency. You will have multiple corner frequencies in particular. red line on slide 6. Oh no, you don't have to plot that red line. That red line is just basically the true magnitude plot. That's just for comparison illustration purposes here. You're just required to do the straight line approximation, which is basically the black line. Alright. Okay, so let's move on. If there are any further questions, I'll answer them accordingly. So, what the actual phase plot looks like here is this curved blue line in particular. Like I said, because it's a straight line approximation, it basically sort of approximates the actual behavior of what this curved line is supposed to be. So, it's an approximation, don't expect it to be fully accurate for the phase plot in particular. The approximation for the magnitude plot tends to be a little more accurate than the approximation for the phase plots, as we can physically see here. Alright, so for your homework, there's been a slight modification to the initial system function that we had here. I'd like for you guys to actually attempt this in particular to obtain the magnitude versus frequency graph and the phase versus frequency graph. One thing to note though is that instead of starting at the 0 decibel line, remember now that because we have this constant value here, the start point is going to be different for that magnitude plot. The phase plot is basically going to be unaffected because constants basically don't contribute to anything towards an angle throughout the entire plot. And because this is a positive constant, and we saw in yesterday's lecture for anything that's a positive constant, the phase is just going to be 0 degrees. Alright, that basically brings us to the end of our second Bode Plots lecture. If there's anything else that you need to ask in this point in time regarding the material of the lecture, please ask so now. Otherwise, I'll be moving on to our final Bode Plots lecture for today. Alright, it doesn't seem like we have any further questions. So, one particular type of question that you get in like in your finals and exams in particular is that we will give you an HFS complex system here. And then we'll ask you to find the relevant straight line approximation, magnitude, and phase plots regarding this HFS system. So the same steps that you just saw in today's lecture are the same steps you will take in order to obtain the final answers for the magnitude and the phase plots in particular. What you need to pay particular close attention to is that when you're doing the magnitude plots, for each one of those lines that you're plotting before the poles, in between the poles, and after the poles, please write down the resultant gradients of each one of those lines. As well as for the phase plots, don't forget to write the resultant angle equation. Those actually contribute towards marks throughout the entire question. So for the magnitude plot, and I'm repeating this, make sure that you write down on the magnitude plot the resultant gradients for each one of the lines for the resultant plot. And for the phase plot, do not forget to write the angle equation because that also contributes towards marks in the question itself. Alright, so let's move on to the third lecture. and our final lecture for today. Alright, so this lecture is basically going to be dealing with an effect that is known as resonance that you may see in Bode plots. And in particular, because you may be dealing with second order Bode plots, once you start encountering resonance, that means that the system equation itself is going to be changed accordingly to reflect this resonance in particular. So you need to observe the effect of this resonance here and how do we accommodate it in the system equations. Or if we do encounter a system equation, how do we know that the system itself has some resonant factor in particular? This goes back to when we were talking about second order systems, where we had the damping factor zeta, and that's what's going to be playing a very important factor here in determining the resonance of the system itself. So we're moving backwards a little bit to the general second order system equation in this form here, where we had omega naught being our natural frequency and zeta here representing our damping factor in particular. We know that zeta here needed to be in between 0 and 1 for a generally stable system, and then if it was less than 0 it would have been an unstable system. If it was more than 1 it would be a very stable system, or critically stable as of such, regardless. But for our purposes here and for this lecture, we're going to be focusing only on the stable system here, where zeta is going to be lying between 0 and 1 in particular. So if we convert this general h of s equation here into the j omega domain, we get its resultant form, and then we rearrange the equation accordingly, we can get it in terms of its real components on the denominator and its imaginary components here as well as of such. The numerator here is just basically a constant value, as we saw, because that's just a here and that omega naught squared. If we rearrange it, when we do the division, that omega naught basically goes onto the denominator in particular. If we try to find the magnitude of this, it comes like if we square each one of these individual terms here, and then we do an overall square root. So a squared, the square root of that is just going to be a. But then the real part here is going to be squared, and then that's going to add to the square of the imaginary part here, and we have to apply the square root in particular for the magnitude. Similarly, what we need to observe is, once we have this resultant magnitude equation here, we need to go to extreme values of omega to obtain what's going to be our resultant decibel values. So when omega approaches 0 in particular, this here will just become 0, and this here will just become 0. So the entire equation here will just result to 20 log of a, because the magnitude needs to be represented in decibels, so that's why we took 20 log of that value. When omega approaches infinity, on the other hand, that means that the entire equation here, when we take the logarithm of it, it's going to be 20 log of a minus 20 log of omega divided by omega naught all squared. And because of this square value here in particular, that is going to represent that same effect that we saw when we had in our first lecture, when we had powers of s on the denominator by itself. And we basically saw that once we have powers of s, that would be minus 20 multiplied by n, where n represents the power of s accordingly. And because this is a square term here, that's going to be minus 20 multiplied by 2, so that gives us a result of minus 40 decibels per decade in particular. The resultant graph, because we don't really care what happens at the corner frequency for a straight line approximation, means that for everything before that corner frequency, we're going to be at 20 log of a, which is going to give us a resultant decibel value. And for everything after that corner frequency, we're going to have a constant slope here of minus 40 decibels per decade in particular. What happens in particular is that at this corner frequency, we're going to observe the resonance effects in the next few slides. And that resonant effect is going to depend on the value of the damping factor, or zeta here in particular. So we want to see this in particular for the true plots, because the straight line approximation doesn't show us this, but the true plots actually show us this resonance in particular. So if we go back to our magnitude equation here for h of j omega, this equation basically has a maximum when the denominator here becomes a minimum. So we extracted the denominator here, and we say let's let that equal to d of omega in particular. We're ignoring the square root value for now because that square root just means everything here will just go to a factor of a half accordingly in terms of power. So because we have d of omega here equal to the denominator equation, we can find the differential of this accordingly with respect to omega, and we get our resultant equation here. And the reason for finding the differential is that the equation itself has a minimum when that differential of the equation equals 0. And once we resolve that out in particular, we see that we get a resultant equation here being omega equals to omega r, where omega r represents our resonant frequency. And omega r is a function of omega naught here and zeta in particular. So omega r here is going to be equal to omega naught multiplied by the square root of 1 minus 2 zeta squared in particular. And zeta here, take a value in between 0 and 1 divided by root 2, which is going to be 0.707 approximately. So that basically gives us an idea of where we will have a resonance frequency occurring. And the resonance frequency and the resonance effect that you see on the graph only occurs when zeta lies in between 0 and 0.707, which is basically 1 divided by root 2 in particular. So 1 zeta lies in between those two values. The h of j omega graph, the magnitude will peak at some frequency, referred to as the resonant frequency here being omega r. And in most cases, the resonant frequency is very close to the natural frequency omega naught. So once that occurs, we typically use the same value because the difference is going to be very minute. When we actually apply this into the magnitude equation, and we say omega is equal to omega r in particular, maximum resonance represented as mr here is given by the equation a divided by 2 zeta multiplied by the square root of 1 minus zeta squared. And this basically gives us the indicator of what's going to be the maximum decibel value at resonance for the entire graph. And this also holds true for the same range of zeta being in between 0 and 0.707 in particular. When zeta equals to 0.707 in particular, this equation here will resolve such that there will no longer be any maximum resonance in particular. So the true plot basically gives us an idea of where this maximum resonance occurs. So once we obtain MR here, we take 20 log of that MR to obtain this maximum resonant decibel value for the magnitude plot in particular. So we know what the maximum magnitude is going to be in particular for this magnitude plot because of that resonant frequency that occurs here in particular and that value of zeta contributing as our damping factor. We also know that in the previous slides, the resonant frequency tends to be very close to the natural frequency, so we just basically say they are approximately equal to one another, and that just basically resolves the equations as of such. For the phase plot, if we did the angle equations in particular, we'll get this complex minus tan inverse of a lot of complex components here involving the natural frequency and the zeta damping factor. But what we want to observe in particular is that what happens at extreme values of omega and what happens at the natural frequency. So when omega approaches 0, this entire angle equation here will just be 0 degrees. At the natural frequency, the entire angle equation here will just resolve to minus 90 degrees. And then when omega here approaches infinity, the entire angle equation here will approach 180 degrees. Oh, oops, I made a mistake on the slide here. This is supposed to be minus, 1 second, 180 degrees. Right. So basically, everything before that corner frequency in particular, it's going to be at 0 degrees. And everything after that corner frequency in particular, it's going to be at minus 180 degrees. And the true plot basically gives us this nice S-shaped graph, but because of the straight line approximation, we're represented by this sharp vertical transition instead. What we're going to observe is that, depending on the value of the damping factor, That actually is going to change the shape of this true plot in particular. And this is actually how we can actually see the effect here in particular for when we have varying values of that damping factor. So when the damping factor is like really small, we have a maximum peak here giving us our maximum resonance at that resonant frequency. And at the same time, with the phase plot, we approach more and more towards the straight line approximation that we saw in particular. As the damping factor increases in value and it's going to be less than 0.707, we approach more and more towards the actual true plot where the resonance is decreasing throughout the entire system. And once you cross 0.707 or 1 divided by root 2 in particular, there's no longer any resonance within the system throughout the entire magnitude and phase graphs. So you'll just get your nice straight smooth Bode plots in particular for magnitude and phase as of such. Alright, so seeing that we had the resonant frequency equation omega r and the maximum resonance equation mr, for your homework, I want you guys to obtain what's going to be the corner frequency, the fall off rate, the damping factor, and the peak rise and fall at resonance in particular. Because this equation here is a second order system, you can map it to the general second order equation system itself, and you can obtain the values of omega naught being your natural frequency and the damping factor immediately for zeta as of such. Alright, so that basically brings us to the end of our Bode plots topic in particular. And okay, before I go, I will basically give you guys one of these answers here. The fall off rate here, because this is a second order system, it's going to be minus 40 decibels per decade throughout the entire thing after the corner frequency. And before the corner frequency is just going to be 20 log of 100 here in particular to see what's the starting point. But the gradient there is going to be 0 decibels per decade. The corner frequency you can obtain because this factor here is going to be 2 zeta omega naught, and this factor here is omega naught squared. So there are a lot of practice questions for this topic, especially in the past papers in particular. Once I do start putting up past papers, I will put up the relevant solutions so you guys can see how you can actually attempt such particular questions, and how you actually can read those graphs when you encounter them, and how you can extract the zeta components and the omega naught components in particular, and you can formulate your own system equations from reading the Bode plots just from watching them. So once I start putting up past papers and solutions, you guys will actually see the method for how you actually resolve those regarding the practice questions. Right. Are there any particular questions on this lecture or on the topic of Bode plots in particular? Please feel free to ask them now. No, I mentioned that I will not be able to do next problem set live with you guys because of the time constraints. Basically what happened is that we lost a week because of a directive from the University Council. So instead of the semester being 13 weeks, I think it's now 12 weeks, so it's ending a lot sooner than I thought. So because I lost that 1 week, normally in that 1 week time, I would have been doing a lot of practice problems with you guys as of such. But if time permits, and once you guys don't have anything scheduled, that session can be totally optional. And if you guys want that session, I am always available to do that session in particular. Also, if you have breaks in between your exams, we can also schedule practice sessions accordingly as well. You can just write me an email, or you can message on the forum indicating that you want a practice session on these available dates and times, and I'll see if I have free time at that point to accommodate you guys. If I don't have free time for the suggested dates, I will suggest the dates and time accordingly when I am free, and see if you guys are also available as well, so you can actually do this practice. There is one more problem set I do need to upload, but like I said, I want to be able to do it live with you guys. I will upload the problem set, and I will upload the solution to it immediately, so you guys can actually start attempting it and verifying your solutions with those problem set questions. Now, as problem set questions in particular, I will be focused on the Fourier series and Fourier transform. But for the Bode plots and for the future topics of Routh-Hurwitz and discrete time systems, there isn't really a problem set associated with those. But the past papers I do eventually upload on the My Learner webpage. You do get solutions for those as well, so you can actually see how to attempt those as of such. If you are having problems with those particular questions, like I said, once we can work out some sort of scheduling, I will do an optional session here right here on YouTube, and we can do those questions in particular live so that we can see how to work through them. And you can actually get some practice in and verify to see if you actually attempted the questions correct and where you're making your mistakes and whatnot, and how you can rectify them. Right, any further questions? Alright, it doesn't seem like we have any further questions, so if there are any further questions, please leave them in the comments down below. Or feel free to email me and ask your questions accordingly. Once I am available, I will reply to them and give you guys feedback. Next week's topic is going to be on the topic of stability and the use of what we refer to as the Routh-Hurwitz criterion. And the Routh-Hurwitz criterion question that comes in the final exam tends to be 10 marks out of the 100 marks for the entire final exam in particular. So that also is a sort of important topic as well. However, the Routh-Hurwitz topic is not very complex, and it's basically a lot of repetitive instructions that you basically keep on doing throughout the entire evaluation. There are just only like 3 special conditions you need to pay attention to in particular, but it's one of the easier topics that you will encounter in this entire course. So we'll be doing that in particular next week, and then the last lecture for next week will be the introduction into discrete time systems. And then after that, the following week after, we'll be moving into the evaluation of the discrete time systems and its relevant transform known as the Z transform. So in particular, that means the last class that we're going to have is on November 24th. And that's going to be the last topic in particular. After that, it will be any scheduled practice sessions that you guys are able to attend that are going to be entirely optional if you wish to attend them in particular. Once you guys are free in particular, we can always work out something schedule-wise, and I can make time to make sure that I can be available to run these sessions as requested. If I am not available, I will make a suggestion as to when I am available, and hopefully everyone is free around that time, or we can work out something in particular as to when you guys will be free on the next available date, and we can run those optional sessions in particular, because it'll be quite helpful if you start doing like practice regarding like the past paper questions and so forth, and you have some sort of verification to know if you're on the right step or not. Alright, so like I said, next week we'll be focusing on the topic of stability, and I'll be introducing you guys into discrete time systems. And the week after, which are going to be our final lectures, we'll be moving on into the Z transform in particular. So until then, take care, be safe, and I will see you guys soon on next week Monday. Later.